Hello, my name is Shazrin Shah bin Raja Ehsan Shah. I am a PhD candidate from the Department of Biotechnology Engineering. I am currently under the supervision of Associate Professor Dr. Sarina binti Sulaiman, and today I will be presenting my research proposal with the title Development of Moving Bed Biofilm Membrane Bioreactor for Treatment of Palm Oil Meal Effluent. The palm oil industry is a very important industry in Malaysia. In fact, Malaysia is one of the largest producers of crude palm oil in the world. The production of crude palm oil consumes large amounts of water. For every ton of crude palm oil produced, approximately 5 to 7.5 tons of water is being consumed, of which half of that gets converted into palm oil meal effluent. Palm oil meal effluent, or POME as we simply call it, is a highly polluting effluent. We can expect to see COD values of up to 50,000 milligrams per liter for POME. Because of this, the discharge standards for POME is highly regulated. So mills are monitored stringently to adhere to the discharge standard set by the Department of Environment. Typically, the treatment of POME is done in biological ponds or lagoons, and these ponds can be fairly large and require a lot of area because the retention time is fairly very long. Because of that, the treatment scheme that is conventionally adopted by palm oil mills faces challenges like high sludge generation and also high operating costs due to the long retention times. The membrane bioreactor technology combines the membrane technology with the bioreactor technology. So essentially what is happening is the biological degradation of effluents and the continuous separation of treated effluent being done simultaneously in one unit operation. So researchers have found that membrane bioreactors to be a promising technology for effluent treatment. In fact, recently there have been a few commercially developed membrane bioreactors to treat effluents and even sewerage. So the advantages of membrane bioreactors are shorter retention time and higher quality of the treated effluent. The retention time can be manipulated by controlling the MLSS values because this will have a direct connection to the microbial activity within your reactor, whereas the quality of the treated effluent can be tweaked by changing the properties of your membrane. These systems require relatively smaller acreage compared to other biological systems, and because of the high quality treated effluent, it can be incorporated as part of resource recovery, especially when you are talking about water recovery. However, as with any membrane systems, you can expect that there will be challenges due to fouling. So fouling is inherent problems to most membrane systems because as the system progresses, you will find solid particles being deposited on the surface and causing the pores to be blocked, and as you go along you will find that the flux will be reduced and you will require higher transmembrane pressures for your operation. Recently, you will find many industries adopting the moving bed bioreactor technology, or simply we can say MBBR. What's essentially happening is biocarriers are being introduced into bioreactors. Biocarriers are small particles or large particles that provide surface area for microbial growth, or this microbial growth can be also called biofilm. So what's essentially happening is you are trying to increase the microbial activity by increasing the concentration of microbes in your system. With conventional suspended solids or suspended growth, you will be dependent on the value of MLSS, or the concentration of suspended microbes within your system. By introducing biocarriers, it is found that the concentration of microbes in your system can be increased significantly. Furthermore, recent studies have found that the growth of microbes on biocarriers are more stable compared to suspended growth. This has directly resulted in the reduction of sludge for systems having biocarriers. So to date, there have been very few work looking into biofilm being coupled with membrane bioreactors as a means to reduce fouling. However, no studies have been conducted so far on very challenging effluents such as POME. And recently, the development of polymer called polyvinyl alcohol, or PVA, as beads have been found to be very suitable to be used as biocarrier. The characteristics of PVA being almost nutribuoyant, I believe the specific gravity of PVA is around 1.02 to 1.03, means that there will not be a requirement for additional agitation to achieve homogeneity in your bioreactor, apart from the sparging that you would expect to be available in common reactors. So in summary, we can conclude that the conventional biological treatment systems to treat POME has two main problems. The first is the high sludge generation, and the second being the high retention times required for treatment. Membrane bioreactors, or MBRs, have two advantages. One is the high quality of treatment effluent, and the second is the low footprint required. However, MBR systems are prone to fouling, which means that you will require a higher transmembrane pressure to retain your flux values. Biocarriers in moving bed bioreactors have been introduced recently, even at the commercial level, to increase microbial activity within bioreactors. Polyvinyl alcohol, or PVA gels, have been studied and found to provide superior characteristics for microbial growth for effluent treatment. So the combination of the membrane bioreactor and a moving bed bioreactor will be the focus of this work. The development of an MBB-MBR system is hoped to be able to produce a system that can treat POME having less sludge generation, and at the same time increased efficiency with a lower footprint. Furthermore, the reduction in sludge and energy requirements will mean the carbon equivalence emission can be reduced as well. Having said that, this study will have four main objectives. The first objective is to design a moving bed biofilm membrane bioreactor to treat palm oil meal effluent. The second objective is to optimize the operational parameters of the MBB-MBR system for treatment of POME, such as biocarrier type, biocarrier loading, and hydraulic retention time. The third objective is to evaluate the incorporation of moving bed biofilm as a biofouling control method compared to conventional membrane bioreactors. And the final objective is to conduct an environmental feasibility study for the developed system by comparing conventional systems with the MBB-MBR systems in terms of carbon equivalent. Next, let's look at the scope of research. For the activity involving the design of the MBB-MBR system, we will start with the membrane selection, where we will be looking at several membrane molecular cutoffs, or MWCOs. Next, we will be conducting the optimization studies, where we will be looking at the critical flux and identifying the optimized transmembrane pressure, or TMP, for the MBR system. We will also be looking at optimizing the removal efficiencies of the BOD, COD, the total solids, and also the total nitrogen. We will also be conducting fouling studies, which involves the evaluation of the flux profiles for the MBR system. We will also be looking at the cleaning process and storage process of used membranes, and we will be assessing the membrane life and the duty cycles for each membrane, because this will directly contribute to the knowledge of feasibility studies. Also, for the preparation of the PVA, we will be looking at the immobilization of microorganisms by using the activated sludge from an established biological pond. The biggest scope of work will probably come from the membrane runs, where we will be assessing the performance of the MBB-MBR system. Once we have a baseline, we will be comparing this with the MBR systems, or conventional MBR systems. We will not be running identical runs using MBR systems. This is because we will be comparing the baseline data with literature values on MBR systems treating POME. We will be looking specifically at the BOD values, COD values, and total solids and total nitrogen, the removal efficiencies of each of these parameters. We will be comparing the hydraulic retention time, or rather the possible decreased values of the HRT, which I'm hoping very much. We are also looking at the comparing the flux values for the MBR system. Again, I'm hoping to see a flux increase by introducing the biofilm on the biocarriers. I'm hoping we will see a flux increase. Next, one of the important aspects on the membrane run, we will also be looking at the fouling profiles, or the fouling behavior. This is crucial because we are hoping to see significant delay, or even a significant delay actually on the onset of fouling on the membranes due to the PVA gels being introduced into the system. As I said before, we will be looking at literature values for POME treatment using MBR, and these values will be used as benchmark, which will be comparing with our developed MBB-MBR system. The final part of this research is the evaluation, or rather a feasibility studies on the developed MBB-MBR system, where we will be taking a life cycle approach, or LCA approach, to estimate the carbon equivalent generation for MBB-MBR system compared to conventional MBR system, and also the conventional biological treatment for the system. Again, this will be done against literature values available. This part of the outcome will be important to distinguish the offset, or rather the reduction of CO2e, let's call it, by running MBBR systems compared to conventional microbial systems to treat POME. This will be in line with the government's move to make the palm oil industry more sustainable. So if we recap, looking at the research that is being proposed here, we are hoping the MBB-MBR system will be able to mitigate and reduce challenges in the conventional POME treatment systems. Specifically, we are hoping that this will be able to provide mills with systems that have smaller footprint. We will be able to reduce the sludge generated by the treatment systems, and we are hoping that the MBB-MBR system will significantly reduce treatment durations, which will directly reduce the operational cost on palm oil mills. The high quality treated effluent coming from the MBB-MBR system will open up opportunities for resource recovery. For example, the treated water will be able to be recycled for other purposes within the plant. The immobilization techniques of microorganisms on the PVA will be able to open opportunities for further resource recovery. For example, specific microorganisms can be introduced into the systems to support production of biogas or biohydrogen. The entire research can be broken down into 4 main phases. We can start off with the sample collection. We have not confirmed the exact site for collection of POME, but we have identified a few plants in Selangor, and currently we are negotiating to see which plant will be the most suitable to supply POME for the work. The first phase of the research will be the characterization of POME. This will be an important section to ensure that the baseline values shall be comparable with the values available in literature. The second phase is the immobilization, or the preparation of the polyvinyl alcohol beads, which will be used in the system. I think this will also go hand in hand with the experimental setup design. In the third phase, the third phase will be the longest phase for this study, which will involve the membrane runs. Finally, in between, we will have the evaluation process for the MBB-MBR system before we go into the final phase, which is the environmental feasibility studies. After, or simultaneously, we could expect article writing and also thesis writing. The main materials that will be required for this research is of course pomade. So we will be collecting raw palm oil made effluent or pomade from a plant somewhere in Selangor. As I've said before, this is to be confirmed. The exact location will be confirmed. Activated sludge or pomade, we'll be collecting the biomass or MLSS from an established biological pond from the same plant, from the aerobic and anaerobic regions, and this will be used for immobilization of the PVA beads. The membranes, we have selected the polymeric ultrafiltration and microfiltration membrane. We will be using PVDF membranes. This is the outcome. This decision is the outcome of the literature that we have surveyed, where PVDF is found to have robust characteristics which will be able to withstand the pH from raw pomade. The biocarriers that we have selected is the polyvinyl alcohol in the form of beads, and this will also be purchased and used directly. The experimental setup is not very complicated. On the picture on the leftmost picture, you will find the loops of hollow fiber ultrafiltration membranes, and this will be ported in the membrane bioreactor, where you can see the blue circle. So it is ideally a tank where membranes will be ported out, and these membranes will be connected to a peristaltic pump which will draw out the treated effluent. The control systems will be attached, and this will typically control the level of working fluid in the tank, and also the peristaltic pump speed. I've also included on the rightmost a picture of the PVA beads that will be used. This typically looks like a styrofoam balls that you will find in packaging material. The statistical design and statistical analysis, I have conducted or looked at this only preliminarily for now. This will be redesigned in the second semesters when we have established the exact input parameters that we can vary. Because, for example, even though the molecular cutoff, the MWCO of membranes, is a numerical value, but this value cannot be controlled, so that might not be a parametric input, whereas the critical flux and the biocarrier loading, whereas it can be optimized, but these are also parameters that are not easily controlled. The responses are quite established. We are looking at the removal efficiencies of the BOD, COD, total solids and total nitrogen. But because of the input parameters, I would say that the design of experiments and the statistical analysis need to be rediscussed and re-established with my supervisor before we can decide whether we want to take this approach for this particular work. At the end of this research, we are targeting to develop a successful MBB-MBR system to treat pomade effectively. We are looking at optimizing the parameters for the MBB-MBR system, and we are targeting to increase flux, also increase removal efficiency, reduce sludge generation, and of course by optimizing the parameters, we are looking at maximizing the membrane life, and also reduce the requirement of maintenance for the system. Finally, we will be identifying or estimating rather the carbon equivalent generation for operating an MBB/MBR system, and having a CO2e value will allow the environmental footprint to be established for operating an MBB/MBR system, and this will be a very useful information to make a decision on whether this technology will be feasible to be included to make the palm oil industry more sustainable. So I hope that the presentation has been clear, and thank you for your time. If you have questions or would like more information on what I'll be doing, I have included my contact information on the slide. Thank you for your time.